Good afternoon, everybody. So I will present this work on indeed visual crack detection in steel structures with convolutional neural networks. This is performed mainly by Andrii, one of our PhDs in our group. So generally, civil infrastructures are inspected through visual inspection. Is the most common, at least, type of inspection that is performed. And in general, visual inspection is recognized to have some drawbacks, mainly relatively low reliability and high cost for trained personnel, relatively high cost, potentially breach closure and hazards and risk for the workers that have to sometimes climb structures. The low reliability of visual inspection is, or let's say the reliability of visual inspection, is generally characterized by probability of detection group. That's true actually for every kind of inspection method, where the crack size is related to the probability of detecting that crack. And we can see in this graph that is from literature that let's say a crack that can be reliably detected with the probability of about 90% has roughly a size of 5.5 inches, but we can also see, let's say, the scatter of the reliability of this inspection, which is generally high. So the aim of our work is to potentially aid visual inspection through interpretation of data by artificial intelligence, in particular convolutional neural networks. That can also is also an enabler for remote inspection, for example, micro remote consumer drones, which are becoming more and more common. Our methodology is based on indeed the convolutional neural network, which is based on UNet, and is characterized by a deep supervision layer and the Kompanets backbone, which is the descending layer. Is in fact an encoder-decoder network, and yeah, it's a bit tricky. It's not trivial to go through the details in this presentation, but it in principle is indeed based on UNet and Kompanets blocks for the encoder. Then the information that are retrieved by the encoder are let's say put together with the layers coming from the decoder, and then in the end we are able to let's say have as output a binary segmentation map. We have a training dataset which is composed by 1,200 roughly images of crack patches, of containing cracks, and 540 background patches. I will explain this concept later in the presentation. And then after the output of the neural network during the training process is evaluated using a test subset, which is composed by 140 patches with cracks. We have 152 high-resolution images of cracks in steel bridges. And in order to train the neural network, we have to annotate this data. So we did that with an automatic segmentation tool, which we have developed, which is based on geometric image processing, in which basically we point the crack ends, and then through a sort of tracking, edge tracking algorithm, the crack is segmented, and you can see here an example of segmentation. However, this kind of image, which is roughly 12 megapixels, is very computationally expensive for the convolutional neural network. So we cannot feed this entire image for training purposes. We estimate that we need about 200 gigabytes of RAM to process the entire image, and our, let's say, the graphic card that we have at our disposal at only 40 gigabytes. So what we did is that we divided the images into batches, and this highlights a a second problem, which is peculiar for this kind of application, especially metallic structures, where the number of crack patches, which are the green ones here, is significantly smaller than the amount of background patches, and this causes a data imbalance problem. Actually, it's peculiar for this kind of application because if we look in the literature for dataset, for example, of cracks in asphalt or in concrete, cracks are generally way more visible at a larger crack opening, or let's say the surface. So this problem is rarely encountered in other applications. Here you can see that, for example, the number of crack patches is about 6.5% in total over the entire data set. And this causes problems with the training of the neural network because sometimes the optimization gets stuck in some local minimum, but also we experience instability of common loss functions which are used to train the neural network. Because in principle, it's very hard to correct for this 93.5% when only 6.5% is actually giving information. So, I mentioned stability of loss function. Very briefly, I want to highlight what is loss function and how does that work. So we have our training data, we feed the training data to the neural network, and given the output of the neural network, we evaluate the loss. And the loss is in fact a scalar that is, let's say, indicator of the performance of the neural network. And we iterate this process by updating the parameter and using a training algorithm which is available on the used one, Adam. What does that mean in other terms? Well, you can see here a background patch, so basically an image without cracks. This is what we could be happy with as a result of the neural network. It's not perfect, but it's a good segmentation. So there are some false positives which are detected, but we don't aim for perfection. And this is instead a bad segmentation with a lot of false positives. So every feature that might look like a crack is actually recognized as a crack. What we see is that by using the dice score, we actually have the same value of the loss function for these cases. And using BCA and dice score, which is another loss function, we also have, we have somehow a small gradient, but it's not enough for the optimization algorithm. And in some cases, by using the focal loss function, we can get some more gradient, although this depends on the parameter of the focal loss function. But in general, we either experience a quick saturation of the loss function or a low gradient. And we should spend quite some time in optimizing the parameter of the focal loss function in this case, which is a pretty time-consuming job. So we came up with the idea of inversion of loss function, where basically for this is a dice loss function, where basically we for background patches we train the neural network to be a background detector instead of a crack detector. In short, the inversion of the loss function can be summarized by this statement. And we see that in case of using a dice loss function with inversion, we see a more significant gradient that enables us to carry out the training of the neural network. Ultimately, we evaluate the results of the neural network in terms of dice score, which is an indicator of the, let's say, the number of pixels, the ratio between the number of pixels that are actually belonging to a crack, that are detected as crack. So as intersection of these two ground truth prediction over the total number of crack pixels. The higher the dice score, the better is the performance. We can see this is a result slide showing some results for basic UNet. The second neural network that we compared with is a neural network that has been used for cracks in asphalt, and the third is the one that we proposed. We can see that the performance in terms of dice score are better for our neural network, and this is mostly due to the training strategy, use Adam training algorithm in other cases. other training algorithms are used, and specifically the improvement is attributed to the loss function with the inversion. Talking about dice score, it's a bit difficult to visualize what the high or low dice score mean. Well, this is an image of a weld with a crack present, this mark. And this is the annotation. I think for due to resolution problem and so on, we don't see the continuous line. Basic unit will predict something like this. Conic, the neural network from the literature, sometimes can detect these markers as distractors, detect them as cracks. And in our work, instead, we obtain a high dice score for this feature, which is comparable to the annotation. However, as I mentioned, it's not perfect because also in other cases, we are not able to get rid of, for example, this arrow, these marks are sometimes detected as cracks. So there is still some work to improve the performance. As a general conclusion, our proposed neural network is based on UNet with the Kompanets backbone and deep supervision. For now, at least with our dataset, outperforms literature. The other neural networks proposed in the literature for these tasks. However, we recognize that indeed segmentation of cracks in seed structures poses different challenges as compared to other materials. The biggest problem we are dealing with is the false positive detection, as I mentioned. So there are too many crack distractors which are not identified as background but as crack pixels. As an outlook for future work, we would like to improve this aspect related to false positive detection, and in particular, we aim to do that with the two-stage procedure, where we first have a neural network for detection of potential hotspots, and then only locally perform a segmentation, which is also very time-consuming task. And we started predicting some PLD curves for visual inspection, for inspection made through this neural network. You can see here in red, which per now is comparable to visual inspection. In particular, this is the PLD curves that I showed you before. This the dashed, the gray one, is the one that is reported with the VGX. But in this, let's say, in the definition of the PLD curve, we recognize that the quality of the detection really depends on the resolution, and in particular the number of pixels per millimeter. So we have to improve on this aspect and collect more data. And that's all. Thank you.
Thank you for your very interesting presentation. Now it's time for questions or comments from the audience. Okay. Thank you.
Yeah, thank you so much for the talk. I think it's a very relevant topic of this automatic inspection. You didn't say anything about data augmentation or how you like exactly split the training from the test data. So it would really interest me, like, what your approach was for that one. And as a second question, did you also try to quantify how certain your network is for the prediction, so like in the direction of uncertainty prediction?
So for regarding the first point, well, I didn't show it here in the slide, but we do some steps for data augmentation. In particular, sometimes we mirror image or we rotate images. So we have steps for data augmentation with some probabilities. So sometimes we do mirror, sometimes we don't mirror, and so on during the training process. Yeah. Regarding the second question, so the outcome of the neural network pixel by pixel is not binary. So where the segmentation map is a binary map, so other pixels are either 1 or 0, the actual outcome is non-binary, so we set a threshold of 0.5, and whatever pixel is indicated with the value higher than 0.5, we associate that to 1. So we did associate that to crack pixel, and whatever is below, we have to deal with non-crack pixel. In terms of probability and scatter, yeah, we can do that on the POD curve. We can estimate the scatter of the POD curve. We didn't really do it because it's huge. In that sense, especially because the images are so different in terms of hardware that took the image and in terms of distance from the car. So we want to improve this aspect before coming out with the
So maybe a comment on this probability side. There is an output between 0 and 1, right? But they are really pseudo probabilities. So the model will overestimate its certainty simply because you just train 0 and 1. So it will always like try to be close to 1. So if you want to do real uncertainty quantification, to do something more elaborate, but maybe we can talk about that.
Yeah. But this is a second step. So this is not included in the training of the neural network. So after we take another subset of data, and we were from the PLD quantification, subset of data the neural network never saw, and to do this. Yeah.
Yeah.
Another question?
Thank you for the lecture. I know nothing about this field, and I was wondering how do you decide that a false positive is a false positive?
Well, we do that by comparing. Oh, well, we can do it here. We do that by comparing the outcome with the annotation. So the annotation is a truth, or is the best representation of the truth we have. And for example, this is indicated to be cracked, but it's not cracked, so it's a false positive.
And is that for every?
It's done pixel by pixel, and for every edge.
Okay. You have many of those actually, because how many cracks or not?
In this case, it's one crack. So we have one crack, which is, so part of this detection is correct, but part of it is not correct. And this lowers the value of the dice. So,
Thanks.
Another question? Okay.
Thank you. Very relevant, yes. I'm wondering about the data that you use for training. But a couple of questions. Were the cracks always straight? Were the features always perpendicular to the crack? Were the cracks kink or?
no, the data set is pretty diverse, so it's always a bridge structure, so it's always most of them at well. But the images are taken with also different lighting conditions. For example, in this case, this was taken in the evening, so this is artificial light. And also images are sometimes taken with the different lighting conditions and so on. So we tend, let's say at the beginning, we had to rely on what we got, because these data sets are not, there is no data set in the literature. This is, before at least we published this data set. Now that we are collaborating with asset owners, we go together with them at inspection, and we tend to take images with diversity of light and diversity of camera position and so on, recording this kind of information.
And the last one, I didn't get that part. Did you threshold them with the intensity?
Sorry?
The threshold. The threshold.
Mm-hmm.
What do you use for threshold? Is it the light intensity or some edge detection algorithm? Or?
For annotating.
No, for the threshold to filter the image.
The threshold is
To filter the image, I see that you apply a threshold.
No, I don't understand the question. Sorry. We do apply. So when the segmentation comes out of the neural network, pixel values are not 0 and 1. So they are between 0 and 1. So whatever is below 0.5, we select to be white, and whatever is like,
Thank you.